So let us start for week 11 discussion of Galois theory. Let me share my screen first. So, okay. Yeah. So in this week, what is done, that is you already have seen in the class. So let's begin with solving some exercise questions. Okay, so the first question is about x, an element which is a real number given by root 2 plus square root of 3 plus and so on up to square root of n or some n, which is bigger than, of course, equal to 2. Then degree of field extension qx over q. This is 2 power pi n, where pi n is number of primes less than or equal to n. Okay, so we will come to the proof of a part. Let's see what next part says. X is same again, is primitive element. This X is primitive element of field extension root 2 root 3 root n attached to Q. Okay, so now if you see here in part B, let me say part B is enough. Part B will follow. Uh, A follows from B, and the fact that Q root 2 root 3 root 4 root 5 and so on up to root n. This is same as Q root 2 root 3 root 5 root 7. I'm just writing primes up to n. Okay, just some p. Why this is so? Because since m, which is less than or equal to n, and m not prime, m, if m is not prime, if m is not prime, then m can be written as product of primes which are less than or equal to n. So root m can be written in terms of, let's say, if m is okay, if m is just, let's say, p1 p2, maybe r1 r2 pk rk, then root m can be replaced by root p1 power r1 and so on root ek power rk. So this is argument for this, that only primes are enough to define this field extension. Okay, non-primes can be written in terms of primes. Okay, and so yeah, first of all, we did this now, and the fact also uh, degree of extension for q root p over q, this is of degree 2, and if you add extra primes, like we have already seen in the seventh week lecture, that if you have different prime than p, then q root p root q, this field extension over q has degree 4. Okay, and so on. Here in this case, because these primes are different up to p p is prime, this p is prime just less than or equal to. So and so on. This follows the q root p1 root p2 for distinct prime root pk. In fact, over q, this degree of extension is equal to k, 2 power k. Sorry, yeah, 2 power k. So a follows from here. Now we have to show that. Now we coming to part 2. Okay, I hope part 1 is clear, right? So what part B says? Let me write that. Part B says qx, which is q root 2 plus root 3 plus and so on plus root n. This is equal to this. And now this is explained here. Here, this is explanation for that equality. And now following this, we have that qx over q, this degree of extension is nothing but 2 power pi n. Pi n counts. Pi n is the number of primes less than or equal to n. That is what's written here. P 2, 3, 5, 7, and up to p, which is the prime just less than or equal to n. Okay, so this is 2 power 2. This is 2 power 1. Number of prime you attach distinct prime. They counts the degree of extension. Okay, 2 power of that number of times. Okay, so this at this part. Uh, this this line is from week 7. Maybe second question or first question. Question 1 maybe. I don't know. This part. There we have shown for distinct primes or distinct co-prime, relatively co-prime numbers. If you attach one by one, okay, so degree gets doubled, okay, each time. So for example, here it was 2, then here it becomes for two primes, we are getting 4, and then we'll get 8 like that. Okay, so A part is done now. Let's see part B. What part B says, uh, so that if x is already given, field is primitive element of field extension. We just have to show that we must show, we need to show q root 2 root 3 up to root n. This is same as q root 2 plus root 3 up to root n. So if you remember in the same week 7 question where we had distinct primes, we have already seen, we have similarly, we have already seen something, some for distinct primes we have seen this relation. We have already seen that for distinct primes, P1, P2, Pn, we have Q root P1 root P2 root Pn is same as Q root P1 plus root P2 and so on plus root Pn. Where we have seen this? In week 7 only. Week 7 maybe question number 2. So uh, I will show it here also some similar something like that. But here we have, here these are not primes, right? So we have to see what would be, what can be done. So this inclusion is obvious, this part, right? Let me write this field to be K, this to be maybe M. Okay? No, because this is obvious. I'm just writing some notation. We can write it as M and we can write it as K or L, whatever. Let's say K. So since each root 2, root 3, root n, all these belongs to M, this implies their sum, root 2 plus root 3 plus and so on plus root n. This also belongs to M, and hence and Q already is contained in M. So Q root 2 plus root 3 and so on plus root n, which is exactly K, we are denoting. This is contained in L. Sorry, M. Now, for the other part, we have to think about how to do this. Okay. So for this, we have to see. Uh, we'll just show that y root 2 belongs to K. We'll just show. We'll show root 2 belongs to K. Similarly, others for others, root I belongs to K. I equal to 3 up to n will follow similarly. So, how to do this? So that so here we have this extension M, and here K, and downward we have Q. Somewhere here we have Q root 2. Okay. Oh, wait. Here we have K, and K is over Q. So here we have Q root 2. Okay, so let me write this down here. Now we have to solve this part, right? That Q root 2 is contained in Q. K. This is our question. If this, we just need to solve Q root 2 belongs to is subset of K, then we are done. Right? How we'll see this? Let's try. Because M over Q is Galois extension. Is that so? M over Q is Galois extension. How? So for this, I think it is Galois is because this is separable by default. It is separable extension. Oh, it might not be. It might not have been done in the class that Galois extensions are separable. Maybe done in the next week, but yeah, it is separable because characteristic of all these fields involved, all the field in fact is zero. Separable extension. And moreover, it is not just separable. M is a splitting field of M is a splitting field of the polynomial. This polynomial product of mu j q, where mu xj, let's not write xj, mu xj, j running from 2 to n, where xj is same as root j. Okay? So take product of these polynomials. and then M is the splitting field of this polygon. Okay, hence it is normal also. Normal field extension. So separable and normal field extensions are Galois extension. Uh, yeah. So here in particular, what is M exactly? M is this. Okay. We'll see in the next page. What is M? M is Q root 2, root 3, root 4, and so on up to root n. And this is same as this is already from we have done in the part A. Why this is so? Q root, I will write just P1, P2, P3 in place of 2, 3. This is just root 2. Okay. So root P2 up to root PK, where where K is nothing but pi n, number of primes. Okay, less than or equal to n. So these are all the primes less than or equal to n. We are taking their square roots. Okay, so this is your m, and now what we are taking, what is odd automorphism to, let me write automorphism of Q algebra of m. What is this? What is order of this group? Order of this group is what? So I'm just saying it is 2 power 2 power k, and this is also 2 power pi n only, and this is nothing but degree of extension also, right? Part A, degree of extension is just equal to, okay, degree of extension is equal to that number it will follow afterward. So we cannot use part A, right? Because part A follows from part B. Yeah, sorry about this. Uh, what I wanted to say here is this, that this is clear. Why? Because let me write any sigma, which is automorphism of it. If sigma belongs to automorphism of M over Q algebra formula, then what we see here is that sigma sends root P1 to plus or minus root P1 only. No other choice for uh, where P1 can root P1 can be sent. Okay, you understand this? This is because root P1 has root P1 has, in fact, root Pj, root P1 has minimal polynomial x square plus oh sorry, x square minus p1. And now, if this is your minimal polynomial, sigma sends root of an irreducible polynomial to sigma sends root of irreducible polynomial over Q to root of the same polynomial. Okay, so P1 has no other choice, so it will go to either plus root P1 or minus root P1. So what will happen to other PJs? Similarly, other PJs will go to plus minus root PJ only. So sigma can be defined like uh, any sigma can define on PIs, root PIs. Any sigma can be completely defined sigma, which is K algebra automorphism, sorry, Q algebra automorphism, can be completely defined by where root pi goes. Okay, because root pi's form a basis for m. Okay, good. Sigma is such. Now, how many root pi's are there? And each of the pi's root pi's have two choices. So, how many? This implies exactly the by counting method automorphism of m over q. This cardinality is nothing but 2 power p1 p2 pk, right? K polynomials for k, sorry, for k primes we have, for each p we have two choices, so it will be 2 power k uh, choices of this kind of uh, automorphism sigma. Okay, so this is our cardinality. And now anything else left? And what is degree of degree, this degree m over q, this by decomposing this way, that m is, let's say, q root p2 and so on root pk, and q root p2 pk over q root p3 q, sorry, root pk, and so on up to q root pk over q. Okay, so each of these degree of extensions are two. Yeah, this is this is for in this, because p1 p2 pk are different times. So this is from week 7 question 2, week 7, maybe q2 or q1, just see it from there. uh, this degree of extension becomes 2 power k also. So this implies that m over q is Galois extension. Now what we want to show, if it is Galois, that q root 2 is contained in k. So This is subclaim. Maybe let me write it as this, and this is explanation for that. Explanation why it is Galois. So now coming to the proof of claim, we are not forgetting our claim that q root 2 is contained in q root 2 plus root 3 and so on up to root n. This is our claim that we had left here to show this part. Okay, this is difficult part than the first part. Okay, so let's see what we can do here. Consider H, which is subgroup of Galois group, Gal n over Q, such that sigma fixes this x, sigma of x is equal to x, where we are not forgetting what x is. X is just this element, 2 plus 3 plus and so on plus 4, and this is defined. And defined other subgroup, this is subgroup of Galois group, which is collection of those sigmas, those automorphisms, such that they fix just root 2. Okay. Sigma of root 2 equal to root 2. And now we will see what is the relation between H and H prime. And then we'll use Galois correspondence. Okay. Good. This is also subgroup of Galois group. And any sigma, okay. So sigma fixing X, how sigma is defined? Sigma is defined on PIs to go to plus or minus any sigma. This is for any sigma, plus minus root pi. Okay. But if you see here, uh, sigma yeah, any sigma is such a defined if sigma belongs to H. If sigma belongs to H, then what happens? Sigma of root 2 plus root 3 and so on, root n, these are fixed, right? Root 2 plus root 3 and so on up to root n. Now, if you see what is happening in root 2, root 3, so so what is happening to root 2, that will decide what is going to happen to root 4, because that is multiple. So we just have to see where for primes. For primes, we have already seen what sigma does. Sigma either takes root pi2 plus root pi or minus root pi. And here we'll see where it sends root 2. Maybe it sends to root 2 to minus root 2. We don't know. Okay. But whatever it is, that will be let plus minus 1. It can be anything. So first of all, let it be write like plus 1 or minus 1, both together, maybe alpha. Okay. Okay. Alpha is a variable at some choice. Okay. So what happens here? Uh, if okay, I can I should not write like that. If you see from here, then my claim is if sigma belongs to S, it fixes this, and then sigma of root pi is exactly equal to plus root pi. Okay? It cannot take minus. Okay, why is so? Since these are all real numbers and we can compare them, right? If it takes some, if uh, sigma takes sigma of, let's say, root p1 or root p2 or whatever, root p1 maybe is equal to minus root p1, then what happens to this value? Uh, After applying sigma, it will become minus root 2 plus root 3. It becomes plus root 4 because root 4 is minus root 2 into minus root 2. Okay. So minus minus becomes plus, it becomes root 4. Okay, this is our where root p1 goes like this and so on. Somewhere it will become like whenever it root 8 will appear or root 6 maybe, yeah, root 5 is as it is minus root 6. Why minus is coming? Because root p1 is a factor here. That is why. That's how we do here. Good. Now what? Why root 4 is positive? Because root p1 is 2 times factor here in root 4. So like that. Uh, After all, it becomes this is less than or equal to this value, right? If you take even modulus of this, take positive number, this is explicitly less than if somewhere minus appears. Okay, and this is contradiction because sigma fixes x. So mod of sigma x x should be same. Sigma x is equal to x implies sigma x, this mod is same as mod x. And because mod x is already positive, all elements, all the terms in the sum are positive. So x is just mod x is just x. So this is a contradiction. So it is better that sigma is identity. What sigma does? Sigma is identity. So sigma is just identity. Identity on M. Okay. So yeah, this is okay. This is good. Something which fixes this element fixes every element. So by Galois correspondence, what we have? H is trivial. This implies what is fixed? M H. Fixed by trivial element. This is whole of M, right? And what we have seen here, yeah, yeah, correct. From here, we don't require that Q root 2 is contained here. In fact, whole M is contained here. It is just shown that, okay, let me write in different color. So the whole M is contained here because automorphism which fixes Q root 2, H is also fixing the subfield of M, which is K. Subfield K of M. So M is equal to K. Because in Galois correspondence, what we have, one side uh, subgroups of subgroups of Galois group, and this is one-to-one correspondence with order reversing subfields or intermediary fields. Galois group, let's say gal M over Q, intermediary subfields. This. So this is one-to-one corresponding. And what is the relation? Any subgroup H goes to MH, or this is same as fixed field of M by H. And what is the other relation? Any subfield where any E goes to this side, Galois group of M over E. Okay, so yeah, good. Up to now, I hope you understand this because H fixes H is identity. So H is only the L subgroup. H is trivial subgroup which fixes M, and H is also fixing K. Why? Because only elements which fixes K is identity. No other element fixes. So H is also fixed. Okay, sorry. Um, yeah. So in this order reversing one-to-one correspondence, K is equal to L. Right? So okay, let's see what next we have. So first part is done. First part A, part B is done. So no need to write this. Okay. We have directly shown that K is equal to L. We'll show that M is equal to B. And we can delete this. Yeah, so first part, two parts are done. Now part C. What we have here we have here A1, A2, AN integers which are not given to any relatively co-prime, but they will be co-prime because whenever you attach root alpha, okay, when alpha is not in Q and you attach root alpha to Q, it will become degree of extension will be double, just double. If you are attaching just root alpha to Q, where alpha is a real number, it will be 2 degree extension. So if you attach one each time root alpha prime, root alpha double prime like that, and degree get double. That's all. What to do in part C? We have already given 2 power n is degree of extension. So that field extension is Galois extension, and that this is our primitive element. This is similar to question number. Yeah, that is all we have already done in part A, part B. Further describe the Galois group. Galois group we already described, or here it is just define. We can just define on where root pi goes, right? These two choices we have. So corresponding, what is Galois group here? This automorphism group. This is Z2 product K times product. Okay, that is Z2 cross Z2 cross and so on. Z2 K times. We have already seen this. So, no need to part C is just part A and part B. Parts. Okay, let me write it so that what part C. Since so what happens here? So I'm just writing factorization. Q root A1 root A2 root A3 and so on root AN. This degree of extension over Q is 2 power n. And now if you write LHS once more, okay, LHS can be written this way. Q root A1 up to AN over Q root A2 up to A root AN. This degree of extension, because we are just attaching root A1 only. and everything else is already in the base field here. So what should be degree of extension that we are going to see what will be this. Okay, and this extension can be either trivial or 2 degree extension because we are attaching root of a1. Okay, so root of a1 satisfies x square minus a1. So the degree of extension should be, this is simple extension over this field, either of 2 degree or it should be of degree 1, because a1 might not, a1 belongs to q, then it will be of degree 1 extension. Either if a1 does not belongs to this base field, then it will be of degree 2 extension. So I am going to say that this is exactly degree 2 extension. Okay, so a2 to an over q root a3 to an, and so on. You just multiply these degrees, and the end you just have an over q, this field extension. So this is our, this should be degree of extension less than or equal to 2 and greater than or equal to 1. Okay, this way, and this follows for every where this degree also. So because this would be equal to RHS, which is just 2 power k, this implies that AIs are relatively co-prime, so that their A1 is not from here, similarly A2 is not from here, like that. So this factorization is not unique. Okay, so you write some other factorization, then you write A2 here and rest of thing here. So they will be relatively co-prime. Each pair is co-prime to each other. Each pair is relatively co-prime. So okay, AIs are relatively, um, maybe I should write pairwise co-prime integers. And now what we were showing in part C. This is Galois extension. Of course, it is Galois extension. What are choices of any any automorphism sigma, any automorphism. Send root AI to only 2 choices, plus or minus root AI or every I. This implies that odd order of this odd group automorphism of M over. I should not write M, but let me write it like that. This is different than the already written M over Q. I should write directly Q root A1 root AN. This automorphism group is of 2 power N, and this is also degree of extension Q root A1 up to AN over Q. So this is Galois extension. So this extension is Galois. And what else we want to show? Primitive element is this sum of these individual elements. Further describe the group. So all of them are clear. We already done in the question, part A, part B. So I'm just directly writing what these are. Galois group of Q root A1 root AN. This is nothing but Z2 cross Z2 is n times. And this part is also true. Like once it is Galois extension, identifix only identity fixes root A1 plus root A2 plus and so on plus root AN. So fix of, let me write it as this as M for, and the other one, okay, so better I should write in different color. Let's say this is your M, and K will, let's say K will be this K root 2 root A1 plus root AN. Then fixed field of just trivial subgroup M is M, and fixed field of M by E. This is also K by Galois correspondence. So we have seen this C part also, little bit description for that. Let P1, P2, P1 distinct prime numbers, then describe the Galois code. This is similar to what we have seen, similar to because they are relatively co-prime. Distinct prime is the same. Okay, so in the second question, what we are seeing, uh, L lowercase separable field extension, and suppose that there exists positive number n such that for every x in L, kx over k, this degree is less than or equal to n. Okay, so that the field extension L over k is finite. Okay, L over k is bounded by the same number n which is already existing. Okay, so let's see what part A shows. Mm, Part A, we are given that kx or given n, given that there exists n, because it is fixed, uh, we can just write n naught in natural number such that for every x in L, this degree of extension kx over k less than or equal to a. So this is given. Now what we want to show, L over k is finite. The first claim is L over k is finite. That is, as a vector space, L is finite dimensional. This is what we want to show. That this degree is finite. So for that, let me uh, start with this, that if possible, if L over k is infinite dimensional, what will happen? If L over k is infinite, this degree, infinite dimensional, I'm just saying infinite, then pick something out from k, then pick some x, maybe let me write x1, okay, belonging to L but not belonging to k. We can find such x1 because L is not equal to k and it is infinite dimensional in fact over k. So pick something from this. Then what happens to this degree kx1 over k? This degree is less than or equal to n by default by the hypothesis for n not n. But because we are choosing x1 from outside k, right? So this would be bigger than or equal to 2. And again kx1, and because x1 is algebraic, is this so? Just given that it is separable extension, separable. So very much. Separable. So it is assumed that this is algebraic and every element is satisfying some polynomial. Minimal polynomial exists for every element of L, and that minimal polynomial is separable. Okay. This is how the definition is. L over Kj. So by definition of separable is like that. That algebraic extension is called separable if every element has minimal polynomial and that minimal polynomial is separable polynomial, like that. So it is algebraic. So kx1 over k is finite dimensional in fact, right? So it is not all of L. Kx1 is not all of L. So we can find more elements. Pick again x2 belonging to L minus kx1. Then what will happen? This degree is again bigger than or equal to k x1 x2. So it is x2 kx2 over k, and this is bounded by n naught again, and so on. Continue like this. Lastly, pick, because n naught is fixed. Let me write here some extra thing. Y and stop. Pick xr belonging to L minus k x1 x2 up to xr minus 1. Then again 2 is less than or equal to k xr k whose are a natural number such that 2 power r becomes bigger than equal to n naught or strictly bigger than n. Then what happens to this? this field exists. What happens to k x1 x2 xr? I'm not writing polynomial in, okay, because x1 x2 xr are algebraic elements. We can write like this, okay, a round bracket or square bracket does not matter. This is a field. What happens to this field? What I want to ask is that what is degree of extension over k? How much, how large it is? What is dimension of this? So for this, what happens? Yeah, sorry. Let me write it as, let's say, L. Okay. So L over K, this degree is same as K x1 up to xr over K x2 up to xr. This degree into K x2 to xr, K x3 to xr, and so on. And then lastly, we have K xr over K, this degree. So you see here we have R terms in the multiplication. These are in natural number and each of them are bigger than or equal to 2. Okay, because in this field we don't have x2. So we are choosing less. Yeah, so that is this is how we had chosen. We have no, sorry, we are, so let me start with downside. This might be incorrect, but similar thing, there might be similar mistake in upper side also. So please look into that. What is that mistake? Kx1 over k, this into kx1 x2 over k x x1 and so on. And then lastly we have k x1 x2 xr over k x1 x2 xr minus 1. Okay. So this is correct. But anyway, same trick is used. These are bigger than or equal to 2. So because there are r terms, so this is bigger than or equal to 2 power r, this degree L over K, and this is already bigger than n naught. We have chosen r. So we chosen r like this. Now you see some mistake here. We are getting some contradiction because this was infinite. L, oh, sorry. L is already used here. Yeah. So I should write something else. Okay, this, you see, this is mistake. Let me write it as M. M is finite because x1, x2, xr are well there, right? M is finite and where M lies between L and K. And because L over K is separable, M over K is also separable, and M is separable. Okay, so finite and separable means M can be written as since M is simple field extension. Primitive element theorem is applied on finite and separable field extension. So M is simple field extension over K. So M is equal to K x or some x belonging to M. This implies Kx, so star implies. This is our contradiction because simple field extension, for simple field extension we have degree of extension is less than or equal to A, right? This is our hypothesis here. Okay, so good. Primitive element theorem or yeah, primitive element theorem. Okay, so we have shown that it is finite extension. Now, what else we have to show is that even the degree of extension L over K, this is less than or equal to A. Okay, so okay, good. We'll see this because now since L over K is finite and separable, field extension, this is simple. It is simple field extension. So L is equal to K into Y for some Y belonging to L, and by hypothesis simple extensions are bounded by N naught. So this is proved. Okay, so what says part B, L over K is finite, separable is already given. So it is finite and separable extension. Then there are at most 2 power n minus 1 intermediary subfields E of L. This is this is done. Similar thing is done in the remark. Some maybe week 7. Question 2. Okay, so you can look there. It is given in the remark that what is this? How many intermediate subfield can be there? Okay. When degree of extension is finite separable, we take value of extensions. There is some mistake in, I think, if you see here in lowercase 2 degree extension, it will become just 2. Yeah, it is correct. I was thinking if we can show it directly using previous things. It- yeah, but we already seen this, right? I think I remember something like this we have seen. Like what are, if it was Galois extension, then it is fine. But Galois, this is not given that it is Galois extension, right? It is finite and separable, so L is given by simple L is simple extension, that is all we know till now. Given, okay, this is part C. L over K finite plus separable From here, we just know that L is equal to ky or some y belonging to L, hence L is simple, L or K is simple extension. So from here we see that L is isomorphic to K algebra. K x modulo some f where f is separable polynomial. F has all its distinct roots. Okay. Now what we can see here, it might not be the case that all the roots of f belongs to L. Okay. So what the roots which are not in L, we can attach them and we'll get some uh, field extension. If F, if F is irreducible, this is Galois extension, then there is nothing to worry about. It will be normal extension. All the roots of F will be lying inside L. Yeah. If no, no, I just said something which is wrong. Just think about this cube root of 2. This is finite and separable extension. But what is polynomial for this? X cube minus 2. Minimal polynomial for cube root of 2. But all the roots are not inside here, even if it is irreducible. So I said this, that is wrong. But if all the roots of F are inside L, then between intermediary fields of L over K and the Galois group of L over K, subgroups in the Galois group is one-to-one correspondence with intermediary subfields between L and K. So the number of subgroups, they are very uh, okay. Okay. So no need to worry till now. We'll attach the roots of F here by Kroneker's theorem. What can be done? Kroneker's theorem. Take L prime, which contains L, such that L prime is a splitting field of L prime is a splitting field of F. Then what will happen? Uh, we'll see that intermediary fields between L prime and K, they are bounded by this number. Then they're fine. So what is degree of extension? Degree of F is same as degree of L over K. Okay. And now this is just to point out. It will come soon just now. So this would be equal to, because F is separable polynomial, this is required. So this is equal to V order of this zero set V of f inside L prime where all the roots are lying, and and L prime over K is Galois extension. We have just taken Galois closure. Okay, might be seeing this in the next coming classes. This is called Galois closure of L over K. This is Galois extension. We already used something like this trick before also. Now, if you see, so intermediary subfields, intermediary subfields E R one to R1 to 1 correspondence with subgroups of Galois group, Galois L prime over K. And what is order of, so you have this, what is order of this? Order of Galois group. So what it should be? At least compare with degree of L over K, degree of F. Sorry, L prime. I'm taking L prime. Automorphism of L prime over K. This is anyway bounded by uh, degree of extension L prime over K. So, uh, what I was going to say is that now what I want to say here is we'll consider only those subgroups. We want to consider only those subgroups. This is not required. Actually, this is, let me write this. This is not currently required, but we'll see anything else. We want to take, we want those subgroups. So, okay, here it was L prime. If we want to restrict ourselves and this E, which are contained in L and containing K, they are, this E is one-to-one correspondence with those subgroups which are Galois group of L prime over K. This fixes K and Galois L prime over L. So here, yeah, this is so these subgroups they correspond to this, and any sigma belonging to H can be described as can be described as where it sends roots of F which are not in L. So cardinality of roots in L prime minus L of F is less than or equal to n minus 1. So the yeah, so there so if you have these elements, uh, so the roots not, for example, let's say extreme choice we have for extreme choice. Uh, if x1, x2, xr, sorry, xn minus 1 are roots of okay, so sorry for this. We want to take those automorphisms which are fixing L. So and fixing L, which are not in L and fixing L. So, so there are very less choices of roots of F lying outside L. So at least they are in numbers this much. So cardinality of Galois L prime over L. This is so okay. I think there was some issue with the internet. I got disconnected. Okay. So here, what I was saying is that fixing L, those automorphisms of L prime, which are fixing L, and they're defined on this n minus one objects, and they're very less. Okay. So number of subgroups between these two subgroups, this subgroup and this subgroup, the number of subgroups are very less in comparison with, actually they are, this number n minus 1 is because one root is already in L x, so at least they are in n minus 1. So these subgroups we have to count. What else? How we should count these subgroups? These are defined as automorphisms which permutes the roots of f. Yeah, they are all permutation of the roots. F might not be irreducible. So yeah. So there, yeah, yeah, of course. Nice. I think I understood it a little bit. So what we are counting is that subgroups between these two groups. So any sigma belonging to H can be described as where it sends roots of F. Okay. It will send to root of F to root of F only in L prime. Okay. And there are at most n minus one choices of roots of F lying in L but not in lying in L prime but not in L. So this much roots may be lying inside L prime or very less maybe. And where we are sending them to a roots only, roots of F only. We are just permuting all the roots, possibly. They are automorphisms. Now, sorry, all of this, so sorry. There are some, this description is for this group. Any H can be described as H will occur as Galois group of L over E, L prime over E. Yeah, H is of this moment. For any intermediary field, any intermediary field between K and L, Galois group of L prime over E. So this subgroup lies between Galois L prime over K and Galois L prime over L. So we are counting such subgroups. So okay, I'm leaving this exercise. Okay, I'm just leaving it. It is already proved in some previous week 7. I'm just reminding you once more. Maybe question 2. Okay, look there. I'm not solving this. This was part C. Whatever part there are only. This was about part D. Part C is asking about so that the assertion need not be true when L over K is not separable. L over K is, we want to give a counter example. L over K should be not separable and A fails. A fails means that is even if Kx over K is bounded for every x, L over K is infinite. Okay. Okay. This is what we want. Kx over K, this degree is bounded by some n naught, but L over K is infinite. Now, if you see for characteristic B example, this one, I'm directly writing so that we'll do it shortly. What is degree of extension for this ZP? Or let me write FP. Degree of extension of ZP X over ZP X dot P. Field extension. Okay. What is degree? We have already seen this is degree P, right? Now, what happens if you take ZP X, Y, two variables now, over ZP X power P, Y power? What is degree of extension? Any polynomial in X, Y with coefficient in ZP, I mean rational polynomial. This satisfies something. No? Some they can be written like this because whenever you have f x y, which is lying here, Let write capital X capital Y. If you take this polynomial, what happens to this? This becomes f power x, sorry, f x y power, right? Why this is so? This is just because ZP is characteristic P field, and if you factorize this, you will see only coefficients of f appears, and what which are multiples of terms, different terms inside terms of f, they become zero because they are just multiple in binomial expansion like that. So this is how it is. If it was fxy by gxy, then the whole power p will become gx power p y power p. So if for any f by g, just take for any f by g here, belong, you take this polynomial t power p minus f x power p y power p gx power p y power. So now this is p degree polynomial. This is variable and this is constant. This lies in this field, right? This part. So all the elements here, they satisfy p degree polynomial here. So using this is minimal polynomial. This is minimal polynomial for f by c in ZPX1. Similarly, if you take L is equal to this ZP, T1, T2, T3, and so on, tail extent, infinite many variables. And if you take K is equal to ZP, T1 power P1, sorry, T1 power P, T2 power P, and so on. So, so for here also, L over K is algebraic. Not only this, every element satisfies every element in L outside K satisfies p degree polynomial. But L over K, this is infinite. So this is the example we want to do this for. Okay, so it is almost time. I hope I could do this also. So let me do some simple thing because hint is not given. So let me do something here. A, find primitive element of this field example. We can take primitive element just x. Y, Q, X is equal to Q, X, Y. I want to say this. Oh, no, sorry. So here this is something else. We want something where x also belongs and y also belongs. Okay, okay. So that was correct, right? Because we are looking over q x plus y. I was just saying q x y. This can be written as q x plus y, comma x y. This is our new field. Okay, we are just attaching x here. Okay, this is k, and this is sorry, this is L. This is k. Then we want to find something here so that L becomes k into some t. Okay, so then t is called primitive. Primitive. Here it is x. Why? That is clear because uh, x already belongs here. We just saw y belongs here. Why y belongs here? X belongs here. X plus y also belongs here. X x plus y is constant because x we are attaching to it. If you subtract from here, you get y. Y also belongs to k. This is okay. This is L. So q x y whole thing is subset of k x. Another side is very much clear. This is trivial. We just want to show this part. Okay, so this is nice part. Part is that was simple. If you don't know primitive element, so please see here. I'm just saying we are attaching a single element, we are getting L. So this single element is called primitive element. And why I'm saying x plus y constant here? Because that lies inside K. This this is element in K, and elements of base field I'm just saying constant. So this is already lying in K minus x, or x we are attaching here. So x plus y minus x, it just becomes y, and y belongs to kx. So simple like that. Okay, so let's see part B. Find the number of generators of the group L star. So this is finite field. So finite field stars L star is cyclic. This is cyclic. Order is L star is just 8. So number of generators is equal to phi of it, Euler phi function of it, and that will become 4. And this is also same as number of primitive elements. We have already seen these things if you remember in previous classes. And what else we have here? K x1 x2 xn, irrational function field in n variables. S1 S2 Sn be symmetric, elementary symmetric polynomial. So that this is primitive element of the field extension. Okay, this extension, if you remember, uh, maybe last week's lecture or last week's lecture, that x1 x2 xn over k s1 s2 sn, where s1 is clearly x1 plus x2 plus and so on x. And since this is just product of all these x1 into x2. Anyway, this is Galois extension. Galois extension with Galois group Sn, right? But Sn is noted here, so permutation group of order n. Let me write sigma. Hmm, Symmetric group. Permutation group you can say. Okay, so this was Galois extension, this part C. And so its degrees, let me write it as m this to be L. Then m over L, this degree of extension is n factorial. And if you see what sigma's, what is Galois group of m n over k x1 plus 2 x2, no, sorry, L plus 3x3 plus nxn. What fixes? So let's just attaching this single element to L. And if this Galois group is of order 1, this is Galois extension anyway. So this is same as degree of extension L x1 plus 2 x2 plus nxn. If it is just trivial, what will be the order? If you take order of this Galois group, this is index, I mean this is degree, and we just saw this is 1. So if sigma belongs to Galois group of m L x1 plus 2 x2 plus and so on plus n xn, this means, what this means, sigma fixes x1 plus 2 x2 plus and so on plus nxn. What happens here? Sigma already fixes this part, right? Sigma anyway fixes x1 plus x2 plus and so on xn. Now what left is this x2 plus 2x3 plus and so on, this part. And sigma is an automorphism. So this implies this is not implication. Okay, so now what is sigma? Sigma is actually permutation of x1, x2, xn. Now because we have here only uh, one sigma fixes, now sigma restrictions of this. Sigma is a cycle. Okay, this sigma is a permutation. Sigma is a is permutation of indices. Okay, I should write directly in the first place. Sigma is permutation of indices. Okay, 2 to n. So sigma fixes this if and only if sigma is identical. Sigma fixes, I could write directly here x1 plus 2x2 plus n xn. Sigma fixes this if and only if sigma is identity. Otherwise, if you see here, if x1 and x2 are let's say replaced with each other, so they will not be same. 2x1 plus x2 is not same as x1 plus 2x2. Okay, so it is not the case. So sigma should be identity. This implies that this is trivial. So this much is no need to write this. So this is done. We'll see you next week.